Dear participants of ASMTA 2021, I'm Eitan Altman and I'll talk about splittable routing in lossy ring networks. My co-author in that work were two students, excellent students in my course on routing game. They're called Sami Dalali and Clara Fontaine. It was a course that I gave in Central Supélec two years ago. The work I show here is part of a larger work in which I try to systematically analyze different phenomena that occurs in networking games with different topologies. To describe this area, I need to introduce some definitions. A game is called non-atomic if a single player has a negligible impact on the performance measures of other players. If the actions of a player have a non-negligible impact on the utilities of other players, then we say that the players are atomic. And the game is among atomic players is an atomic game. If a player has to send all its flow within a single route, then the problem is said to be a game which is non-splittable. Otherwise, if each user can split his flow among various routes, it is then a splittable game. I'll be using the term routing games for games which are splittable and atomic. So there are finitely many players, and each one has to split its flow among various paths. The term congestion game stands for non-splittable routing games which are atomic. So each player has to send all his traffic to one of the routes. There are a few assumptions that are made on the cost in routing games and congestion games. Namely, the cost is additive. This means that the cost over a path is the sum of the costs of links along the path. Another key characteristics of these games is the conservation of flow. That is, all the flow that gets into a node also exits that node. In this work, we shall depart from these assumptions on the costs and on the conservation of flow. The simplest topology that can be thought of is perhaps the parallel link topology, which was studied over 100 years ago by Pigou in his book of 1920. So there are two parallel links, and you have to decide how much you send to each one of them. More recent work on parallel link topology can be found by Ordarom and Shimkin, or Kourilis and Lazar, Milstein, and many others. This topology is well understood, including uniqueness of the equilibrium and the price of anarchy. Interesting behavior of the equilibrium were identified in the following load balancing topology that was much studied by Professor Kameda. The load balancing game consists of two n players. The action of each player is whether to go to the direct destination D using a direct path of Si to D, or whether to go there through an indirect path, that is Si to Sj, and only then from Sj to D. The load balancing game consists of two n players. The action of each player is whether to go to the direct destination D using a direct path of Si to D, or whether to go there through an indirect path, that is Si to Sj, and only then from Sj to D. The results, so some of the results concerning this topology are as follows. We still have uniqueness of equilibrium here. There is unbounded price of anarchy, and there is a brass type paradox that was identified by Professor Kameda, in which at equilibrium all routes are used, including the non-direct routes. Here are some references to the study of the load balancing topology. The costs that we have in these examples is additive. It corresponds, for example, to delay. Additive means that over a path, the cost is the sum of costs over each one of the links of this path. In congestion games, a key property that makes the existence of equilibrium easy to solve is the fact that we have a potential game. What happens if we have losses? The game doesn't have potential anymore in general. Cost becomes non-additive over links, and there is no flow conservation. Here are two references that study such instances. We next extend the load balancing problem to the whole line. So this is the line, the integer numbers, or both the negative and the positive integers. So on each one of the nodes here, there is one or more players. The number of players can be random, but the distribution is known to all players. Each player has to decide whether it takes the direct road to the destination, or whether it takes a two-hop route. First to the next node, and then from the next node to the destination. Note that our game here is infinite. There are infinitely many players. The performance of a player depends on the one before it or after it, in a recursive way. The challenge here is to compute the value of the game and the equilibrium as a function of k and of the boundary values. An interesting question to ask here is whether there is a stationary regime such that as k goes large, we converge to it from any initial distribution of the boundary values. Another network element that we'll look at is the ring. So we study routing on a circle. And the problem that we look here is of choosing the direction. So either we go clockwise or anti-clockwise to get from a node to another node. These are quite useful in modeling token rings in communication networks and runabouts in road traffic networks. We next combine a kind of synthesis of both a circular topology, but where the goal is not to go to decide between clockwise or anti-clockwise, but rather to decide at each point whether we route a player to the destination in a direct path or through an indirect path. Now, there may be a random number of players at each node. I now turn to the description of the loss system that we consider in the paper presented to this conference. There are two levels of systems modeling that we shall present. There is a flow level in which routing decisions are taken, and a more detailed packet level modeling which determines the loss and thus the interference between flow from different sources. The decisions of a node concern only the fraction of packets originated in that node which will be routed on each of the two paths available to traffic from that node. Then the actual packets to be transmitted over each one of these paths are selected according to an IID Bernoulli thinning process. The decisions are thus the Bernoulli's thinning parameter. Players and actions. Each node K is connected to a set of n players, denoted by Nk. Each of these players are identified by small n and small k. It has to ship a strictly positive demand phi k to destination delta, which is common to all players. Each of the nk players generates packets following an independent Poisson process. The player decides with what probability to send an arrival that is generated over one of two possible paths to delta, either the direct one or the indirect one. Now, alpha is the vector of decision variables. Alpha kn denotes the fraction of class K flow originating from player nk through the direct path, that is, through the link Decay. We call the vector alpha the assignment or the action vector. For a given demand vector phi, the assignment vector alpha completely specifies the set of flows below. With probability alpha jn, a packet originating from player n in nj takes a direct path to the center, and otherwise it takes an indirect path. It is first relayed to node j plus 1 and is then forwarded to the destination through link d of k plus 1. Now, the model for the loss probabilities. We consider two types of losses. First is an IID losses at the relay, that is on the link between node k and node k plus 1. A packet originating from node k is lost if relayed to node k plus 1 with probability qk. So this is a fixed parameter. Second type of loss is collision losses on the links Decay. These are the links between node K and a destination. Whenever an arrival occurs while there is another packet in service, then there is a loss. The transmission duration of a packet in link Decay is exponentially distributed with parameter μk. The total flow sent to link Decay consists of the superposition of first the Poisson process flows that arrive at node K and are transmitted over Decay, 2 of the Poisson flow originated in node K minus 1, consisting of those packets that were not lost in the relay to node K. Computing the loss probabilities. The total rate of arrival to Decay is given by the expression for Rk below. The loss probability of packets at Decay is therefore Rk over Rk plus μk, and we denote it by pk as you see in equation 1. The cost function. By the same argument, the loss probability of packets at Dk plus 1 is Rk plus 1 divided by Rk plus 1 plus μk plus 1. The total rate of losses of packets of player nk is therefore given by equation 3. In the rest of the paper, we assume that phi k, n, mu k, and qk are constants that are not dependent on k and n. Global optimum. Consider a symmetric multi-strategy alpha for all players, that is, in which alpha kn are the same for all players nk. Without loss of generality, let phi equals 1 over n. Note that this expression for phi corresponds to rescaling time, that is, measuring time units using a constant different than 1 second. Then the rate of arrivals of packets at the links Decay is R equals 1 minus alpha times q. The loss probability on link Decay is then given by the following expression. So the global loss probability is pi equals PL, as we saw above, plus 1 minus alpha q. It is minimized at alpha equals 1, which means that all players take direct paths to the destination. We next compute the equilibrium. Assume that player nk deviates and plays b instead of playing alpha. Let u be the multi-strategy after the deviation. The cost for the deviating player is then given by equation 5. Differentiate jk and u with respect to b and obtain, using maple, the expression in figure 6. Equating to 0 allows us to obtain the best response action b as a function of f of a. This minimizes the loss probabilities of a player when all other use alpha. Then the symmetric equilibrium is obtained by computing the fixed point of the mapping b equals f of alpha. This leads to the expression in figure 6, in equation 6. Figure 2 shows the best response function, and as we see, in spite of its looking very ugly with a lot of terms, it is an explicit expression for the best response, which allows us to go quite far in the analysis afterwards. Here are some numerical examples. We depict in figure 3 the parameter alpha star defining the symmetric equilibrium as a function of the loss rate parameter Q. The following parameters are fixed. N, capital N is 1, mu is 1 as well. As long as alpha star is in the unit interval, then it is the equilibrium. This is the case for Q lying below 0.5012. For larger Q, the corresponding symmetric equilibrium is alpha equals 1. Our work illustrated that we can handle even explicitly equilibria in systems that have losses and that don't have additive costs. The routing game here still turned out to have one equilibrium, a uniqueness property, but it turned out that if we just deviate a little and use the framework of congestion game, we lose this uniqueness property and may have several equilibria. Thank you for attending my talk.